Hello everyone, this is the third lecture of the mathematical module of the mini course on computation. And today we are talking about more on the philosophical sides of the relation between math and computation. Yeah, but before that, let me make some quick announcements. So as you might already aware, yeah, we have a decay of the number of attendance. So from now on, I guess for our convenience, let's switch to Zoom chat from now on. Yeah, although it might not be too easy for me to monitor, but yeah, let's try. And also thank you all for the midterm feedback. Yeah, I will adjust the course accordingly, but looks like most people learn a lot and enjoy the course so far. And also want to reiterate a little bit on the ideas on concluding lecture. So I'll give an overview and discussion in the concluding lectures real quick. And then I also want some of you to show up and present your thoughts, like what you have learned or anything you want to share with the audience, and to increase the diversity of the lecture. So if you are interested in this, please send me an email. Yeah, this will be simple and I can give you more instructions, yeah, once you send me an email. Yeah, and also a few words regarding last week's lectures. Yeah, so from the midterm survey, I can see that some people say that, oh, it's still a little bit hard for them to understand, like, for example, the physics part or the biology part. But I want to tell you, like, it's totally fine. It definitely takes time to do that. And the purpose of this mini course is more like quickly give you a overall feeling and you to grasp the high level story so that you can move on. Yeah, so if you are interested in like go back and review, I still encourage you to focus on high level and don't be bothered too much by the jargons. Yeah, they are just names. And I think I tried to like define all the jargons, yeah, as much as possible in the lectures. So it should be understandable to some extent, but do let me know if you still got confused. And in the meantime, we will also provide more references in the list so that people can check in later, but we're still preparing on that. Yeah, and finally, yeah, don't need to force yourself to get into other fields, like there's 3 different fields. Yeah, so instead, like maybe just treat this as an exposure and listen to your inner sounds on what you really like. Okay, so this is all I want to say. I see some question in the chat. Yeah. Oh yeah, so for the next 3 talks, I think all of them will be available in public. Yeah, so only the previous 2 physics talks, due to they're talking about more frontier stuff, so they hope the talk won't be recorded. Yeah, but from now on, everything will be recorded. But I still encourage you to come to a live session so that we can have interaction. Especially this week, we will have a lot. Okay, anyway, let's get started. So today, the main topic is a reflection about Turing machine and reality. Especially, I want to read out this quote by Einstein. He said, "As far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality." Yeah, so this is maybe something you can think about. Yeah, just want to share. Yeah, so in the mini course so far, we start with the question of asking what is computation? And we saw some of the connection and some basic mathematical foundations through Turing machine and a more modern study on complexity classes, complexity theory. And we also saw lots of connection to the physical world, like through different physics theory, like classical mechanics to like relativity theory for gravity. And finally, we also saw in the biological module that there are lots of, examples, yeah, where like some biological systems or biological objects, they are doing certain kind of computation. So those are more like intuitively are doing computation, and we are asking like, oh, how can we unify all of them? Yeah. So So maybe at this point, yeah, after we saw so many examples, you might ask, okay, so what is computation? Like this is the original questions. Yeah, after seeing so many examples, are we ready to answer this question? But well, I will answer like, well, I can always try to squeeze out some answer for you. Yeah, like from how we see, I can squeeze out a seemingly formal definition. But I also want to argue that by doing that, maybe it's not that illuminating. Yeah, because it's like telling your answer seems to end the discussion. Yeah, it seems like maybe not as illuminating. So instead, in the next few philosophical lecture, actually, we are going to ask more questions. Yeah, so given from the lots of examples we have seen, I want to actually I want everyone together. We can ask more questions and like sparkle more thoughts, and like in the end, maybe all this discussion and questions can lead us to have a better understanding of what is computation. Yeah, so just to give a very overall feeling, yeah, maybe for each field we can ask something like, for example, for mathematics, we can ask, does mathematics really characterize computation? If not, then what's missing? And in the physical world, does the physical world really like can be modeled by computer, or is physical world actually is a computer? Yeah, if so, then so what? Like, what does this really matter? What does this really tell us? And in the biology part, yeah, maybe the question itself also not so certain. What does that mean? But we can see that from all the example we see, yeah, comparing to mathematics and physics, the computation in biology is more elusive and full of like uncertainties and unknowns. Yeah, how can we study or say about computation under such many uncertainties and unknowns? Yeah, so this is just maybe the beginning of asking lots of different questions regarding the three fields we have seen so far. And today we are going to focus on the relation between computation and mathematics and try to ask more philosophical questions and hope this will help us have a better understanding of what computation is. But before we move on, I actually want to make a clarification because later on I'll use lots of word computation. And as a clarification, when I say computation, what I have in mind actually is not exactly what people usually say about like computer science. So to me, computer science is more like a specific implementation or instantiation of computation. And what we really want to discuss, yeah, in this mini course, especially in the next few philosophical lectures, we actually try to think of computation as a more general things. It's not necessarily just the logical, mechanical stuff we implemented. It can be something like we intuitively think it is computation. Okay, so after this clarification, maybe then we can start our journey. And since we are talking about philosophy in this lecture, so maybe it is definitely important to mention about what have been discussed before in the study of philosophy of computation. And surprisingly, at least by some Google search and some quick literature survey, actually there are not too many study or discussion in this direction. So one of the best reference I found actually is this article like almost 40 years ago, like a tour of philosophy of computation. And actually it is a scribes of a talk. Yeah, but I still found lots of the question raised there quite illuminating. So I'll use some of the contents therein as a starting point of our discussion. But I also want to emphasize that this is saying that actually it is a really lack of the discussion of philosophy of computation. There might be some talking about computer science, but for a more high level, there's a general intuitive idea of computation. Yeah, there's really a need of more discussion. So what does the philosophy of computation roughly about? For example, people can ask questions something like, what's the relation between mathematics and computation? And this is exactly like the the things we are going to discuss in this lecture. And maybe you can also ask something like, does computation have to be logical, mechanical, automatic? Is it something that can be beyond that? Because maybe from the original mathematical definition or from the working definition in computer science, computation is something really logical and mechanical. But when we look at biology, it seems like maybe not necessary. Yeah, so is it has to be that way? And if not, and how to study computation? Mm-hmm. And we can also ask about something like what's the meaning of computation? Yeah, because when we talk about computation being really mechanical, maybe it loses a layer of like a meaning and understanding. Yeah, and what can we really say about the meaning and understanding of computation? And finally, yeah, something, this is also quite nature, like especially after people see the physical part. Yeah, is everything doing some kind of computation? Yeah, and if this view of computation about everything can give us new insights to the world, or what does this really tell us? Yeah, so we can keep this on and on, but maybe I'll end with a partially joke quote from this paper. It says like the famous saying of Descartes, say like, I think, therefore I am. And maybe now in this computing era, people can instead ask like, oh, is that I compute, therefore I am? Yeah, so maybe this is a small joke, but you can also think about how like valid this saying to you. Yeah. Yeah, but yeah, before we keep going, continue this kind of philosophical questions, and indeed we will start it in a minute. But before that, I also want to give people a reminder or even a warning. Yeah, at least I sometimes feel that I need to be reminded. Yeah, and especially this is a quote by a famous mathematician called Misha Gromov, and maybe you can replace the mathematics with philosophy in this passage, but let me read it for you. So Gromov said, one may continue indefinitely along these lines, but one has to stop somewhere. Wings of imagination supplied by the power of mathematics can bring you beyond of whatever can be reached by a more pedestrian kind of thinking. But if you fly too high in the sky of math, you may miss your destination down on earth. Yeah, so I hope this passage can remind you like, oh, it's nice to have lots of philosophical discussion. This might bring us farther, but it's also important to remember, yeah, I mean, I hope, yeah, like the end destination we aim for is still down to earth. Okay, so like I hope this is like a opening like for you to think about like in the next few, including this one, the next 3 lectures about like our philosophical exploration. So now let me go back to lecture 1A and 1B a little bit and try to connect our later discussions with the materials we have seen so far. So in lecture 1A, we talk about lots of things centering on these things called Turing machine. And it is really beginning with like in the early 20th century, mathematicians started to want to think about computation mathematically. So they model computation in terms of math and using like function over either natural numbers or Boolean strings to model our intuition of computational problems. And then Hilbert asks these questions of, oh, can there be like a mechanical procedure such that given you any computational problems, you can solve it? Yeah, and in order to answer these questions, people need to capture what does mechanical procedures mean. And in the end, people kind of agree on this definition of Turing machine, which is roughly is an analogy of a mathematician doing calculations, but Turing machine itself has a very formal mathematical definition. And based on this Turing machine, after people agree on that, people think of Turing machine as like a mathematical definition for mechanical procedures, so that they can start to understand like, oh, what kind of computational problem is computable or not. And all this foundation lies in this belief or these axioms of a Church-Turing thesis, which think of Turing machine as a definition, mathematical definition for mechanical procedures. Yes, so after seeing all this, like in the foundation, mathematical foundations of computation, yeah, we might then, I mean, if we want to have a philosophical treatment on that, we can then try to maybe doubt or even challenge the foundation. But what kind of concrete questions can we ask about it? So this maybe can start from the first question I listed also in the email earlier today. Which is like trying to slightly go from the mathematical pure abstraction world to what's in reality. Yeah, in particular, to give a more definition of what I'm saying. Yeah, the mathematical ways of studying computational problem is formally known as something called formal language. In the sense that they try to argue that, oh, our computational problems are something you can describe by formal language. And formal language in hindsight is really just like a function over natural number of Boolean strings, what I said before. But this is just a formal name and it's called formal language. Yeah, but the first question then maybe is like a formal language really captures the computation in reality. Yeah, like especially even just a computation can be done by a human being. Is formal language really capture that? And then further, we can also ask, okay, because Turing machine basically is designed, yeah, to tackle this kind of formal language, and it is a definition for mechanical procedures to solve formal language. Then we can also ask, like, does Turing machine really captures our ability in reality? Yeah, in particular, is maybe mathematician is it can go beyond Turing machine or not. Yeah. So this question is really about, like, in reality, should we go beyond formal language of Turing machine? And if we go beyond, like, what's the extra things we can see and what's the new insight we can get from? Or like, do you think formal language and Turing machine is kind of already enough? And then the second questions we could ask maybe is like is maybe more like a scientific cultural things. It's like, okay, so after Turing, basically people stick with this notion of Turing machine, and the study of the theory of computations is really just stick on that. Especially if you go into, I think most of the university, their department of computer science and the subgroup of theory of computations. Yeah, they all like basically all study theory based on the Turing machine. But does this kind of pure mathematical study of a Turing machine is really enough? Yeah, and this maybe even have two layers of question. First is the connections to the other applied field of computer science. Yeah, does this kind of pure mathematical study of theory of computation connect to what the real applied computer science is doing? And maybe the second layer is more about all philosophical discussion, like is all this kind of mathematical discussion on computation is enough? Yeah, is this really captures the reality? Yeah, so the second question is really about asking about like computational reality and math. Yeah, so now I encourage people, yeah, I'll give maybe, I don't know, 4 or 5 minutes or 3 to 5 minutes for people to type down on the chat. And meanwhile, I'll read out some of the comments people write on the chat, and I hope these questions can make you to think a little bit about what's the material seen before, and think about like how you interpret it, and etc. Yeah, so feel free to type in the chat, and after like people think about it and have a discussion a little bit, I'll answer these questions on like from my personal view, and also provide some extra more materials, yeah, to foster the discussion. Yeah, but now I hope people can think before I talk. And while people are typing, maybe I can also explain a little bit on what this code is about. So actually, this code has a cute story. So actually, this is a quote I used in my statement of purpose when I applied for PhD. Yeah, like at that time, I'm a very innocent kid. Yeah, I enjoy the mathematical thinking a lot, and I'm afraid of physics because I feel like, oh, in physics you have to match what you see in reality. Yeah, it is so scary. I need to satisfy the natural laws. Yeah, but in mathematics or in computer science, I can be so free. Yeah, I can create things, etc. So this is actually the very first quote I use in the first sentence of my statement of purpose when I applied for a PhD. Yeah, but you can also see like after 4 or 5 years, I also have grown up. Yeah, and my philosophy also changed a little bit. Yeah. Okay, I saw Mustafa say something. Yeah, he said pragmatically, like through practical experimentation, it seems that math is capable of capturing reality in terms of describing, predicting, and even explaining it. So I guess Mustafa probably refers to, yeah, at least in practice, in like what we care about, like the real experiments or like real implementation, mathematics seems to be enough. Okay, and Ethan says, I think the formal language and Turing machine helps to compartmentalize and contextualize the power and complexity of these devices. If we were to go further potentially into a more applied math direction, we would be looking at more dynamic situation, which would constrain the definition of Turing machines. Yes, this is, let me think a little bit about how to interpret what you say. I see. So I guess what you're saying is like maybe even in some situation we need to give Turing machine more constraints because Turing machine itself, the definition is very flexible. Yeah, but if we want to really study specific like say a physical system or some biological phenomena, we need to add extra constraints to make it more reasonable. Yes, I completely agree. This is very insightful. Yeah. Let me read one more, and due to a time limit, I probably cannot read all of them, but I encourage you to still keep posting it because we will have the Zoom chat in the end. I can post to everyone. So Justin said, if we agree that physical world is doing computation, we mostly use real or complex number for describing physical variables. However, Turing machine is mapping integers to integers. How can Turing machine capture all computation if physical world is doing computation using real complex number? This is an amazing comment, and I'll try to touch a little bit today, but I think maybe in tomorrow's, okay, actually Wednesday, in Wednesday's philosophical lecture, this will make more sense. But indeed, I think what Justin said is like what Turing machine doing is inherently digital. But in the real, like in the reality of physical world, maybe things work in an analog way, meaning that the stuff happening in the physical world is like continuous, maybe not digital. Yeah, so how can you use the digital objects to like fully capture and continuous objects? So maybe a quick answer is that people also study some continuous version of a Turing machine, etc. Yeah, but let's dig into this problem deeper in the next lecture. Okay. So this animation should come earlier. Okay, but so now I'll move on. But I still encourage you, if you have thoughts, please type in the chat. I'll look at it afterward. So maybe for me, at least for me, trying to answer these two questions regarding the mathematical definitions of computation and the relation of computation to reality. I actually want to start with an analogy to theoretical physics. So in the second module, we saw that the development of theoretical physics or physics in general is like probably like we start from some Newton worldview, like a three-dimensional Euclidean space, and then we move on to like this kind of phase-based understanding of classical mechanics and go to quantum and gravity theory. Yeah, so in this like historical developments, yeah, people like some philosopher, yeah, observe things like it seems like the historical development of physics is like not very smooth and continuous. There's like this kind of things called paradigm shift coined by a famous philosophy of a science philosopher called Thomas Kuhn. And the idea is like he said he observed the development of physics actually is very discrete. It's like, oh, people use the Newton paradigm for a long time. And suddenly we switch to a totally different paradigm, like maybe classical mechanics. And suddenly maybe switch to another paradigm, maybe like a quantum computation. So the new paradigm might still explain lots of stuff in the previous paradigm, but they are so different. And it's like after the paradigm shift, most of the like scientists or physicists then move to the next paradigm to study things under those framework. So I guess using this analogy to theoretical physics, I guess my questions to the first questions regarding like computation and mathematics and Turing machine, I would say like perhaps, yeah, we are currently just living in the paradigm of Turing machine and formal language. Yeah, for now, they seems to be like a very useful model and do things pretty well. And we have a very fruitful result. And same, but probably we could potentially, actually we are living in the era of like Newton, because for people living in the Newton era, they also think Newton laws and the Newton's gravity theory is amazing. It already probably captured everything. But since we are living at this current era, we don't know what's happening in the future. So it could be the case that there actually can be a better model, but just we don't know right now. So perhaps this is not the end of story, but also I'm not smart enough to propose a new one yet. Yeah, to replace like this Turing machine and formal language, etc. And to answer the second questions about like computation and reality, I also want to digress a little bit into the philosophy of science. Yeah, as I mean, also as an analogy or like learn from their experience. So in the philosophy of science, yeah, they mainly thinking about physics, by the way. Yeah, they maybe ask questions, something like, oh, what qualifies as science? And maybe they will also ask, oh, how reliable are scientific theories and what's the ultimate purpose of science? So we can replace everything here by like a computation. Yeah, what do we really mean by computation? And like what's computation theory is like really makes sense, and what's really what the understanding of computation really refer to reality. And in the study of a philosophy of science, there are actually lots of different branches. Yeah, here I just selected the 4 main branches through the philosophical view. Sorry, for the like historic development, and I skipped a lot of them. But the point here, I want to give you a little bit background and some context in your mind, so that maybe you can use like what people have been used in the study of philosophy of science, and to rethink about like what's the potential in the study of philosophy of computation. So let me quickly, although this will be very intense, so I don't hope you all to get all of them, but just to give you a flavor of like what all these 4 branches of philosophy of science is roughly saying. Yeah, so So feel comfortable to don't understand all of them, but I just want to give you a feeling, and I encourage you to look up for more materials later. So the first branch of philosophical science is the most ancient one probably. Is called hypothetical deductive model, and the concept is very simple. It is saying that what is called as science? It is just like we build hypotheses and then do deduction and then kind of empirically verify, etc. So this is really like how we learn from high school, for example, and also lots of field of more applied physics or biology. Yeah, they are roughly doing all applied math. Yeah, but later on, roughly in 1930, some physicists and mathematicians, they are not so satisfied with just doing hypothetical deductive model. They want to refer more to the reality. Because in the hypothetical deductive model, they don't really tell what is truth, what's regarding as the reality in the world. This is also really related to our questions. Yeah, so then there's a new branch of philosophy of science, which is called logical positivism, sometimes known as logical empiricism. Yeah, they build on top of the previous hypothesis deduction model, and they want to talk about something more about reality, etc. But in their study, they kind of try to isolate the theoretical term and the observational term. And what do I mean by theoretical term? It is more say our mathematical deduction, our analytical analysis, etc. And the observational term is what we observe in the world, what we can do experiment on. And in the logical positivism, the central idea is try to separate them. Yeah, they encourage people to, they think of we pursue each the theoretical term and observation term respectively. And maybe in some condition, we can talk about their connection. And they also kind of accept the gap between what we can say about reality and theory. So basically, their central idea is a theory, they accept the potential gap of theory from the reality. But because they still want to pursue this kind of unity of science, so they also allow themselves to do some purely deduction in a theoretical term, while in the meantime, they accept that those theoretical approach might not really refer to reality. So this is quite popular, in the early stage, of philosophy of science. But then people trying to have lots of criticism, but then you really cannot say what is counted as truth and what is not. Yeah, if you separate the two, yeah, you don't do a verification of what your theory is about, then those theories seems to be useless, seems to be intellectual games. So that's why later on there's these two other branches of more modern philosophy of science came up. The first one is called by the way, these are examples. Maybe just my personal thinking, they might belong to that. Yeah, sorry to that. Yeah, and for scientific realism, their response to the critics to logical positivism, it's they have the belief of there's actually an ideal theory for explaining the reality for the real world. So they first have a belief that there's something there, there's something ideal called ideal theory that can explain reality really well. And their goal is exactly trying to find the ideal theory. So they have some criteria for what they think of ideal theory should be, but they don't know what it exactly look like. And what they are doing is they'll build up lots of theories based on experiment, etc., and try to match their criteria of ideal theory. And in another branch is called instrumentalism or pragmatism. Yeah, their view is more okay, yeah, why bother by the reality and truth? Yeah, they only care about whether the idea, either a theory of observation, can be effectively explaining and predicting the real world phenomenon, etc. So yeah, so there are lots of debate, and here I just want to give you a feeling of what has been intensely discussed among like philosophers and also some physicists and mathematicians about how to view the connection of scientific theories and reality. And also here, I also want to emphasize that, although I say so many branches, but usually the case is like, oh, it's not like, oh, I belong to this branch, so I reject all of them. It's more like for a philosopher, you might have, probably will have different philosophy on different areas in science. Okay, so hope this give us some materials to think about stuff. And if we go back to our original questions, yeah, then yeah, like our original questions about like the relation between computation and reality. Then I would say, in my personal view, I feel like the theoretical computer science way of studying computation actually is more like logical positivism. Yeah, it's like we base on like this kind of Turing machine and church Turing thesis, and then keep doing deduction, like etc., and kind of separate reality and the theory quite cleanly. And in the meantime, the more applied the study of computer science, maybe it's more on the instrumentalism side. So I guess here, although I'll provide my response in the next slides, yeah, but I hope all this discussion of philosophy of science at least provide us some language and materials to think about the questions and to put like our own solutions into some framework to help us foster this discussion. Okay, great. So now finally, let me answer, give my answers to the first two questions, yeah, using what I have been like discussed and explained to you. So in my opinion, yeah, like Turing machines or the formal language formations, yeah, to study computation, I think it is quite legitimate. Yeah, it indeed have lots of intellectual merits. But it's also important to keep in mind that it's probably just a specific paradigm we are currently living. And it is possible to have a better paradigm, but just like due to all intellectual limit for now, we haven't seen that. And then for the second questions about the connection to reality, I think my response would be I would try to support or encourage the development and of like maybe a slightly new, different way to study computation. Yeah, like maybe rather than the traditional theoretical CS way of studying, just like a purely like a logical positivism way of based on Turing machine, church Turing thesis, etc. Yeah, we probably should have a new area, maybe let's call it theory of computation, although sometimes people confuse the two. But for this, we think of computation as a more high level object than like computer science. And we trying to understand its connection to reality. So to give like a pictorial explain on what I have in mind, it's like maybe this TCS is a subset, but it's a strict subset of the study of theory of computation. And TCS is a pure subfield of mathematics, but the theory of computation itself is not a strict subset, and it is like interacting with mathematics, physics, and biology. And I hope like people in the field can be open-minded and also have some people to work on like creating this field. And I believe this will be more illuminating in the sense that it will connect it to more connected more to reality, so can like inspire other fields even more. Okay, so this is a short response of me to these two questions. I hope this also inspire your thinking a little bit. So feel free to keep thinking and type down stuff, and you can also email me offline to continue the discussion. But now maybe let's move on to the second lecture of the mathematical module and talk about the next two questions. So just a very quick recap. In the second lecture, we talk about the modern study of theoretical computer science. In particular, people focus on something called complexity classes, which put computational problems with similar consumption of computational resource together. So we saw lots of complexity classes like P, like efficiently solvable problem, NP, BPP, BQP, etc. And then like complexity theorists, they try to study the relation between these complexity classes. And we also saw that in order to really like have a solid mathematical studies, yeah, we kind of need to make some assumptions. Yeah, like we study the asymptotic behavior of the computational problem, meaning that how the resource scale with the input size rather than specific finite size. And we use big O notation and use polynomial time as a definition of the efficiency. In particular, like in Liji's amazing guest lecture, he also kind of justify the reason, like why this assumption is reasonable using some philosophical ideas, like a discussion called the Sohri's paradox. And finally, there's a small weekly related topics talk by Prahlad in his advanced section about four-color theory, where like in the end, this important theorem is actually proved by computer, and the computer proof is like not really comprehensible by a human being. So in the end, people actually write another computer program to check the original computer proof. So based on all these materials have seen, yeah, we could probably continue the question we have asking about the relation between computation and reality more. Especially we can be more concrete. We can ask, oh, this kind of worst case analysis and this kind of asymptotic analysis in theoretical computer science, how to interpret this in reality? Like, yeah, although they admit that they are doing more like pure mathematics and abstract thinking, but how can we still like extract something from them and talk about something closer to what really happened? And also the last questions maybe is even more elusive. It is about like the relation between computation and understanding. Yeah, so I'll motivate this question using the four-color theory in the sense that one critics to the four-color theory's proof is like, oh, the proof in the end is proved by computer. Like human actually cannot really understand the proof. So if you cannot understand mathematical proof, do you think this proof is really proved? And similarly in computation, if you don't really understand, quote by what do I mean by understand? Yeah, if you don't really understand what the computation is doing, like, is that okay? Yeah, do we really have to have some meaning, like an understanding to a computation in order to call it computation? So now I'll pause for similarly for maybe only 3 minutes this time and encourage people to think about these two questions and type in the chat. And then similarly, I'll provide some of my thoughts and end the lecture today. Yeah, so yeah, I'll give people some time, and even I started to talk continue. Yeah, I still encourage you to keep thinking and writing. Yeah, but I also read a little bit on the previous discussion. Oh, also Rayo has a comment on. Ah, okay. Maybe Rayo, I can talk to you offline about why actually instrumentalism and realism actually they are kind of conflicting with each other. Yeah. Also, by the way, I also want to emphasize I'm not an expert in the philosophy of science. So what I talk was my own biased understanding, and actually I think like one of our guest speakers, she's actually going to talk on Wednesday. Zhiqian, she's a more like more expert than me, like in the study of philosophy of science. So I also encourage people, if you are interested in this kind of discussion, you can reach out to her or ask her questions in her talk or in a panel discussion. Mm-hmm. Mhm. Okay. Prahlad said he briefly touched this in his talk, but why should proof be elegant? Yeah, this is something that we look for. Yeah, this is this is actually very good questions. Like what because in the end maybe mathematics or like knowledge in the end is also related to beauty. Yeah, like people kind of only view a I don't know, a proof. You think of a proof, the real proof, it also needs to be beauty. Yeah, so yeah, this probably will also be discussed in Zichen's talk on Wednesday because she's going to talk about beauty actually. Okay, great. There's also lots of discussion, but due to time limit, I probably have to move on. And maybe in the next lecture, I'll provide more time for people to discuss. Yeah, but let me quickly say something about my own response to these two questions. So maybe for the first response, questions regarding like how to interpret worst case analysis or asymptotic analysis in theoretical CS and connection to reality. Maybe I want to emphasize the importance of studying what's meaningful inputs. So in the mathematical worlds or like in TCS, yeah, we have like lots of input assumption, like a worst case analysis, average case analysis, and smooth analysis. I'll explain what these three means in next slides. Yeah, but these things are like pure mathematical definitions, and there's a huge gap between reality. Like those inputs might not really appear in reality. And let me explain a little bit what's the difference between them. So in worst case analysis, this is what people roughly, if I want to have a pictorial image on that, it's like the circles means that all the possible inputs to a computational problem. For example, you can think of the graph coloring problems. So everything, one point here is like a graph to you. And the worst case analysis means that they study every inputs and they focus on the inputs that have the worst performance. Yeah, that consume the most computational resource. And in the average case analysis, they are actually like slightly different setting, but maybe the easiest setting to think about is like they think of all the possible inputs that have equal probability to appear. Yeah, so they have some a priori like a probability. Yeah, having in mind about what's the possible inputs. But due to the ignorance of what's really happening in reality, so what they can do is just assume or every input have the same probability. And there's another things maybe kind of incorporate the two is something called smooth analysis. I think Li Jie also mentioned this a little bit in his talk. And the high level idea is like instead of looking of the worst performance of a point, we look at any inputs and look at the small perturbations, meaning that some other inputs very similar to it, and we consider the average behavior there. Yeah, so this smooth analysis is something like building on top of worst case analysis, but try to make it more closer to reality. But in reality, maybe the input we care about or really what happened actually just a small fraction of the whole all possible input space. So it is very important to me, like to ask about how to model the empirical input that really will appear. And also, although Li Jie argued that it is if you want mathematics study, you probably cannot handle finite problem due to Sora paradox. But I also want to encourage the study of that. So my view and my proposal to answer the question would be maybe we need an independent study of what's meaningful inputs. Yeah, this is maybe worth focusing on regarding like even how to solve the problem. And this is in particular very well studied in physics and biology because they care about more on like specific stuff. So maybe we should gain some like inspiration from them. Yeah. And finally, I don't have too much time left, so I'll just quickly going over my view on like what's the importance of understanding in computation, maybe also in mathematics. So maybe as a starting point, we like as a more like a theory-minded person, we all view like mathematical proof as the golden like a standard for understanding. Yeah, we need a mathematical proof. But if you go into TCS for a long time, you will realize some people prove a theorem using 200 pages paper. It's although it's a sound mathematical proof, but it's still very hard to digest it. Yeah, so does this really means understanding? Yeah, and after I interact with more physicists, even collaborate with them, I realized they also sometimes sacrifice the mathematical correctness a little bit and using some heuristics to argue the correctness of their theorem, and sometimes even use empirical performance. So I guess my response to this, like in the new study of theory of computing, as opposed to theoretical computer science, I think it will be fruitful if people can incorporate all three different methods or even more methods together. So I'm not saying that we are going to sacrifice the mathematical proof, but I'm saying that using multiple methods and multiple way of understanding together, yeah, in different aspects of the problem might help us have a better big picture and insights on the problem. Okay, so just a quick summary. So today we discussed all these 4 questions, and due to time limit, to we don't have too many opportunities for everyone to share your thoughts. But I still encourage you to put in the chat so that I can post it later to everyone. And you are also welcome to continue this discussion afterward. And before our next next talk by Angel, let me also emphasize a little bit. Tomorrow we will have our teaching staff Somya and Avantika talking about some basic in quantum computing. So if you are interested in quantum computing and don't have the like a background before, I encourage you to go to their advanced section. They will provide very approachable introduction to quantum computing. And on Wednesday, I'll give a lecture on the philosophical side of the discussion of physics and computation and focus on these 4 topics. And we will also have our guest speaker Zichen to talk about the relation of art, beauty, and computation. And we will also have an afternoon advanced section by Salvador on like DNA computing and cellular motor, etc. So there's a lot, and you can always check the schedule on the course website. And here are some references. In particular, these first two references is more related to the philosophical discussion today. And you can find the link on course website. So yeah, so I guess this is the end of this lecture, and I'll stay here for a little bit. And yeah, potentially I can also answer and discuss some questions before Angel's talk. Yeah, so thank you all for your attention.